Hi everyone, I'm Dr. Claire Xiong from Micron School of Material Science and Engineering at Boise State University. Here is a brief introduction of my lab, which is called Electrochemical Energy Materials Laboratory. We are interested in using different synthesis approaches such as electrochemical synthesis, wet chemistry, or solid-state synthesis to make a variety of nanoarchitectures and nanoscale materials. We're also very keen on understanding the role of defects and disorder in metal oxide electrodes. We have been working on understanding ion irradiation effect in ceramic materials for over 7 years. Another focus in my lab is interface engineering at the electrolyte interface, as well as within complex metal oxide electrode materials. We have devoted significant effort in developing in situ and operando characterizations of electromaterials, including synchrotron X-ray spectroscopy, Raman, AFM, and so on. Our current focus of applications of these materials is in rechargeable batteries, such as lithium-ion batteries and beyond. So if you are interested in what we do and would like to join us, feel free to contact me and reach out. I'm always looking for great students. Next, my students are going to give you a virtual tour of our lab.
Hi, welcome to Dr. Claire Xiong's Electrochemical Energy Materials Laboratory, where we make batteries. Today we're going to walk you through the process. Every battery requires a positive electrode, and here we make the precursors for that. We control pH, temperature, and delivery of our chemicals into the flask, and they then react to make our precursor.
We then take the precursor and mix them with other materials, which we then press into a pellet. Upon pressing with the pellet, we then heat them up in one of these two sets of ovens. This set of ovens control the conditions of which those materials heat under, while these two ovens just expose it to open air. The reason why we want to heat up the battery is so we can examine the differences in crystallinity and morphology that may arise. Once we heat up the pellet, we then take it to the next stage of the process.
After calcination, the material needs to be put in a form usable in a battery. To do that, it's mixed with carbon and a binder, and then laminated over a foil to be cut and used in the cell later.
Counter to the positive electrode is the negative electrode. Most of our negative electrodes are formed via electrochemical anodization. The anodization is performed in a solution with an applied voltage. Anodization allows us to control the nanostructure of our material and readies it for construction and point stock.
Because lithium is so reactive with air, it'll quickly oxidize, rendering completely useless for our purposes. So we work in an argon-filled glove box under an inert atmosphere. We also work with our electrolytes in here, and the electrolyte is the liquid that sits between the two electrodes, preventing charge transfer but allowing the passage of ions that enable the battery to function. The electrolyte can have an outsized effect on the performance of the battery. So we load our newly made battery into our battery holder. And we load that into our cell cycle. And once that's accomplished, we then run a plethora of experiments to evaluate the electrochemical performance for a battery, its energy density, and its power.
Work in the EEML also extends up here to the MEC 416 corrosion lab, where today we're doing some high temperature, high pressure studies on zirconium fuel cladding for nuclear reactors. From this setup, we're able to connect it to a potentiostat and gain some electrochemical impedance data that can tell us about surface interactions and material integrity for this fuel cladding.
We also look into characterizing the materials we make in the EEML through instrumentation at the Boise State Center of Materials Characterization and the Idaho Microfabrication Laboratory. For example, here is an SEM scanning electron microscope in which we can visualize the surface of our materials.
We use instruments like the X-ray diffractometer here to determine things like the crystal structure of materials so we can understand structure-property relationships.
So we are also working in the surface science laboratory to study the battery materials with the scanning thermal microscope in both ex situ and in situ simulations.
If you are ready for a challenge to develop new materials for a sustainable future, I look forward to meeting you.